All right, I've already written a bit of this one out as well. So we've got our function of ln x, and I can approximate this, or equate it actually, to my Taylor expansion around a equals 1. So that's going to be f of 1, f prime of 1 over 1 factorial times x minus 1 to the first, etc. So I know my derivatives of ln x. I'm going to get ln x, that's going to go to 1 over x, which will become negative 1 over x squared, and then positive 2 over x cubed, negative 3 over x to the fourth, etc. So evaluating at 1, because that's my a value, ln of 1 is 0, and then when I plug in 1, I'm going to get 1 here. And so this is where I got all of these values here. I can summarize this with my nth term is going to be negative 1 to the n plus 1. I need my first term, when I've got n, I need that to be positive. So adding 1 to it to make positive. And then x minus 1 to the n power. I can also note that my nth derivative is going to be, so here's my first derivative, second derivative. So my nth derivative is going to be negative n minus 1 over x to the n. And I should have said here that this is going to be negative n minus 1 factorial. This derivative 3, that should have been negative 6 there, because I'm multiplying my 3. And the negative may or may not be true. That's going to be alternating, so that's going to be based on first derivative was positive, so again, same thing as I had here. And when I divide by the factorial from using my formula for Taylor, that's what canceled out this factorial on top, leaving me with just my n in the bottom. So this bit here is giving me my derivative value. I'm using that when I think about my error term. So I want to approximate ln of 1.1. So I just talked about finding the Taylor series. This is part A. Down here is part C. I'm going to leave you to use ratio test, figure this out on your own. So down in part C, estimate ln of 1.1 accurate to 4 decimal places. Well, I'm going to start by figuring out my error term. So my error term using the nth polynomial will be the n plus 1th derivative evaluated at C over n plus 1 factorial. Over here, I'm going to have my x minus 1 to the n plus 1 power. Well, x is 1.1, so 1.1 minus 1 is 0.1 to the n plus 1 power. I saw that my derivative is going to be my negative 1 to the n plus 1 power, so having n plus 1 here made me have n plus 2. Of course, that could also just be written as n, because the plus 2 is just going to square it and make positive 1. So I could also just have an n there. Over n plus 1, because the factorial cancels with the derivative. So I'll have n plus 1 in the denominator. I'm going to have my c value raised to the n plus 1 power, and then x minus a to the n plus 1 power, so that leaves me just my 0.1. My c value is going to be between my a and my x, so between 1 and 1.1. Well, if I replace c with 1 here, that's going to be a bigger value than replacing with the 1.1. So my 1.1 is going to give me the smaller value, 1 is going to give me the greater value. So I'm going to take this and plug it into my calculator and see how many terms I need to estimate my ln to 4 decimal places. So 4 decimal places means that I want my error term to be less than 1, 2, 3, 4, 5. So 4 zeros and a 5, so I want it to be less than 5 times 10 to the negative 5. So I'm going to put this in my calculator and see how many terms I need to take. So I've done that already. So I've put in my negative 1 to the x power times 0.1 to the x plus 1, divide by x plus 1. I'm looking at my table. If I come over into the values, I can see a more than I see in my table. So this is too much. I don't need that many terms. All right, negative 0.25. So the negative doesn't matter. My error is my plus or minus. So really I'm looking at 2.5 times 10 to the negative 5, which is less than 5 times 10 to the negative 5. So that would work. The one before it is not less than. So that means that I need to take this is going to be the third error term. So I need to approximate with my third Taylor expansion to estimate this accurate to 4 decimal places. So this happens. So this is true for n equals 3. So then I can say ln of 1.1 is approximately, so I'm going to take my third Taylor polynomial. So that's going to be 1.1 minus 1, so that's going to be 0.1 minus a half times 0.1 squared plus a third times 0.1 cubed. What this means that I'm doing is I'm approximating ln with arithmetic. I don't need to know anything about logs to approximate this value. So I can go in and say that, let's clear this out, 0.1 minus a half times 0.1 squared plus 0.1 cubed divide by 3. All right, so this value should approximate ln of 1.1. And sure enough, that's really close. So I can use arithmetic to approximate my logs. Awesome.